We've had cars that can cruise down an empty, perfectly painted highway for years, but the moment you take that same vehicle and drop it into a dense city grid, the system freezes up. Engineers call this problem the long tail of driving. Most of our time on the road is highly predictable and routine, but a tiny percentage of our driving is spent dealing with rare, highly unpredictable events. Imagine a cyclist swerving between a moving bus and a car. It's an interaction requiring split-second judgment and subtle physical negotiation. This forces autonomous vehicles into a massive contradiction. They are programmed to strictly obey rigid traffic laws, but to survive that intersection, they also have to react creatively to human beings who break those rules constantly. For over a decade, developers tried to solve this by choosing a side, either writing explicit rules for every scenario or feeding raw data into a machine learning model. Both methods hit a hard limit. To move forward, the industry had to rethink the entire brain of the car. This diagram shows the knowledge-driven, or rule-based, paradigm. Engineers hard-coded explicit if-then rules and state transition models into the car's computer. When approaching an obstacle, it rapidly searches through a massive decision tree, evaluating every mathematically possible maneuver before picking a path. This graphic illustrates the main advantage of that system: absolute interpretability. When the car evaluates its options to turn left, right, or go straight, the engineers know the exact mathematical reason it made its choice and can guarantee its safety bounds. But that rigidity becomes a fatal flaw. When a rule-based system encounters a scenario that isn't explicitly written in its code, like a person chasing a dog into the street, it panics. It usually just slams on the brakes. A rigid rulebook works flawlessly in a closed environment like a factory floor. On a public road, it is far too conservative to handle the infinite variability of human behavior. The modern alternative is the data-driven approach. Instead of writing explicit rules, engineers train end-to-end machine learning networks on millions of hours of real human driving footage. By watching us, the software develops an intuition for traffic flow. It learns how to smoothly ease into a crowded lane or navigate around a double-parked delivery truck without needing specific code telling it how. Because the neural network teaches itself, it operates inside a black box. It processes sensor data through opaque layers of logic to output a driving path. But lacking mathematical safety bounds, it can hallucinate and dangerously swerve, leaving engineers unable to pinpoint why. Machine learning provides the intuition required to navigate a busy city, but without formal guarantees that the car won't do something erratic, a pure data-driven model cannot secure regulatory approval. To solve this, modern engineers are abandoning the idea of a single solution. They are stacking these two completely different architectures on top of each other to create a unified dual-brain system. In these hybrid pipelines, the system first uses a neural network to read the environment and propose an intuitive driving path. But before executing, the path enters a safety shield. The rule-based framework strictly audits the network's output against hard physical constraints. If the machine learning model hallucinates a maneuver that requires an impossible acceleration or gets too close to a pedestrian, the rule-based shield immediately vetoes the command. It then forces the car to execute a pre-approved, safe fallback action. This stacked architecture takes the fluid, human-like intuition of machine learning and traps it inside a rigid cage of mathematical safety. It finally offers a realistic way to navigate the long tail of unpredictable driving. By having a strict rule checker on board, researchers can encode ethical boundaries directly into the vehicle. Even when the car faces a completely unscripted, chaotic event, the math guarantees it will prioritize pedestrian safety over arriving at its destination quickly. Getting this to work on an assembly line is incredibly difficult. Engineers have to force two radically different software philosophies, one based on fluid probabilities, the other on strict logic, to audit each other in milliseconds. You can't rely on a cloud server when you are traveling 60 miles an hour. Running this dual-brain architecture requires a massive amount of localized computational power housed physically inside the trunk of the car, operating without lag or system crashes. If a generative text AI makes a mistake, it prints a weird sentence. If an autonomous vehicle makes a mistake, a 2-ton machine crashes in a human space. The burden of proof for this technology is magnitudes higher. Securing widespread regulatory approval and public trust is the final hurdle.
We won't get there with pure artificial intuition, and we won't get there with brittle lines of code. We will only get there by building a hybrid mind that balances our human chaos with absolute safety.